Hello everyone, I'm Cuo Zhang from the University of New South Wales, Australia. Today I will present our recent work, Distributionally Robust Operation for Islanded Multi-Energy Microgrids Considering Thermal Comfort and System Frequency Deviations. At the beginning of this presentation, I will introduce islanded multi-energy microgrids first. In this kind of microgrids, electric power and heat energy is generated for local loads. The MEMGs meet a challenge of uncertainty such as renewable power generation, electric and heat loads. Such uncertainties can cause electricity power and heat energy imbalances, impairing customer thermal comfort and maintenance of system frequency. To address this negative impact, this paper proposes a distributionally robust operation method. The major contributions of this paper include an optimization model of islanded multi-energy microgrid operation with new models. Secondly, this paper proposes a distributionally robust optimization method with specific chance constraints. At the right side, we can see there is an islanded microgrid. The CHP plants can support electric power and the thermal energy simultaneously to the multi-energy loads. In this work, we propose a new optimization model for islanded multi-energy microgrid operation. This model involves conventional constraints such as those for the CHP multi-energy generation and also for the micro turbine and gas boiler. Then we develop a new thermal comfort index. If this index is larger than 1, that means the occurrence of overheat. On the other hand, if this index is less than 1, the underheat condition occurs. On the other hand, we also develop a new model for the system frequency deviation calculation. We calculate the electric power imbalances first, and then based on the frequency factor of the system, we calculate the system frequency deviation. And in this model, we want to keep the frequency deviation within the allowed range. With all above constraints and also consider the uncertainty model, we make the final optimization model. This model just wants to minimize the gas usage cost subject to all the constraints. To solve the proposed optimization model, we apply conventional constraint optimization method first. In this method, the occurrence probability of inner quality constraint satisfaction is guaranteed to not less than a confidence level. Then we develop the distributionally robust chance constraints. We formulate the occurrence probability by equation 24 and then apply some transformation on these constraints. Finally, we apply the Hofting-Tail probability inequality, and this paper develops a specific closed form expression for the distributionally robust chance constraint as 29. At last, we did numerical simulations for the proposed method. We also applied one conventional deterministic method for comparison. The simulation result validates the proposed method can efficiently improve thermal comfort level and reduce system frequency deviations, with guaranteed high solution robustness against uncertainty realizations. And in the future work, we also want to apply advanced data-driven distributionally robust optimization method for the proposed islanded multi-energy microgrid operation. Thank you for listening.